How does large-scale atmospheric circulation affect precipitation? So we've got this globe and we've got our flow cells, and we want to consider how this is all connected. So how large-scale atmospheric circulation might affect precipitation. In the area north of 60 degrees north, so above the equator, we have cold air descending at the pole, and surface winds bring this cold air south. Between 30 degrees and 60 degrees, north-moving air at the surface meets the air flowing south from the pole, causing the air to rise and cool, promoting rain and snow along this boundary. Near 30 degrees north, two cells have descending airflow. This dries out the air and results in low rainfall. Sunlight has its maximum heating effect at the Earth's equator, as I keep reiterating, where rising heated air causes locally heavy rainfall. So the pattern that we see is alternating between pressure systems. So starting at the top with 90 degrees, we've got high pressure, and so it's dry. 60 degrees, we've got low pressure, and so it's wet. 30 degrees, high pressure, and so it's fair weather, meaning it's drier again. So we get more precipitation where warm air rises and cools. And that is occurring at the low pressure system. So if we could zoom in, the part that you want to be looking at is right where these flow cells intersect. Okay, so if we could zoom in on that, these flow cells are moving together and up, away from the surface. So when it's moving up and away from the surface, that is a low pressure zone. Remember, because it's like you're picking the air up off of the surface, decreasing the pressure. Okay, as opposed to the other side of that flow cell where it meets the next one, they're coming together and sinking down toward the surface. So if it's moving toward the surface, then we have a high pressure system. Okay, so we tend to have dry air where the air is descending. Air temperature and air. How is air temperature affected by air pressure? So how does the air temperature vary around a high pressure zone? Well, remember, with high pressure, that means the air is sinking. And so if we think about convection, what type of air sinks? The cool air is sinking down towards the surface. Okay, so you're going to find this in a particular area. And we'll get to that in just a second. Around a low pressure system, it's the opposite, right? We're picking the air up. So again, back to convection, what type of air rises? Hot air. So we have warm, moist air rising, and that's what gives us our unsettled weather conditions. So if we look at the low pressure zone, what air masses interact to create a warm front? Well, the warm front is represented by the red line with the little red nubbies, and you have to have warm, moist air moving into cool air. That's what a warm front is. Okay, in contrast, what air masses interact to create a cold front? You have to have colder, dry air moving into warmer air, and so that's represented by this blue line with blue teeth. So you'll see this on the Weather Channel, or your local weather person. The warm fronts and the cold fronts are always represented this way. Describe the weather around a low pressure zone. So when we have a low pressure zone, we know we have warm, moist air rising, and it cools and condenses in the upper atmosphere, and so we get clouds, we get rain, and we get different types of different types of weather, whether it's a warm front or a cold front. So around a warm front, we're going to get a lot of sort of drizzly rain Whereas around a cold front, because you have this contrast between very cold air and warm air, we can get more violent weather, things like tornadoes. So here is another way to look at the warm fronts and the cold fronts. Describe what happens at a cold front. We have a cold air mass moving into warm air, and think of it like a big wall of air, okay? A big wall of cold air. So it moves as one big chunk, and when this cold air hits the warmer air, the warm air sort of jettisons up into the atmosphere, okay? Because this contrast causes it to rise more quickly. And so when that happens, because it's already so cold on the other side, we quickly get that condensing and turning into rain and thunderstorms. And again, this is where we can get really big storms, things like tornadoes. Which air mass is doing the pushing? In this case, with a cold front, the cold air mass is doing the pushing. And what will the weather be like at this location? It's going to have rain and thunderstorms and potentially tornadoes. How does the temperature change on either side of the front? We have cold temperatures moving into warmer temperatures. So where it was warm, it becomes cold. Okay, taking a look at the warm front, describe what happens at a warm front. So in this case, the air mass that's doing the pushing is the warm air mass, and it's moving into cooler temperatures. So this works more like a ramp, okay? So we've got warm air that ramps up gradually over cooler temperatures. And so because it's gradual, we still get rain, we get snow, we get clouds, so unsettled weather patterns, but we don't have those violent storms that you get with the cold front. Okay, so again, the warm air mass is doing the pushing. What will the weather be like at this location? We're going to have rain and snow, but more drizzly kind of rain and snow. And it can be more prolonged. How does the temperature change on either side of the front? We've got warm air moving into cooler air, so where it was cool, it now becomes warmer. Okay, here is a typical U.S. Weather pattern, and we've got our high pressure system up in the north, almost the Pacific Northwest, but not quite, so just still further inland. And then we've got our low pressure zone really in the Midwest. So why does this happen? What's going on? Draw the parts of a low pressure system, your note should say, with the air masses and the fronts. So you've already got the image there. You can just copy that just to reinforce what's going on here. So around that low pressure system, we have warm, moist air coming up off of the Gulf, right? So we've got evaporation occurring when the sun hits the Gulf of Mexico. So all this warm, moist air is moving up towards the pole because that's what warm, moist air does. It wants to move into this colder area. So we get a warm front, and again, represented by our red line with the red nubs. So as a result, we have light, steady rains ahead of the warm front. But we also have this cold, dry air coming down from Canada. So cold polar air comes in, creating a cold front. And so we get showers and thunderstorms, but also along that cold front, this overlaps perfectly with what's called tornado alley. So it's this combination of warm, moist air from the Gulf interacting with cold, dry polar air that gives us the tornadoes that we see here in the U.S. So deadly weather such as hurricanes, tornadoes, and severe thunderstorms are associated with which type of pressure system? Okay, if you look in the upper left of this image, we don't have much weather going on at all. We just have dry, cool air. Where all of the storms are is around that low pressure system. So that's the key. Why? Because you need to have air rising up so that it can cool in the upper atmosphere to form those clouds and create the storms. Okay, I gave you the notes for hurricanes because this is all important information. I want to make sure that you have it. And there's also a little video here. So click on the video and see what it has to offer. Hurricanes expend a tremendous amount of energy which they obtain from warm ocean water. Warm water evaporates, the water vapor rises. As pressure decreases, vapor precipitates as rain, but the air heats up, causing it to rise again. Okay, this is the key. The air is heating up and causing it to rise again. The newly heated, rising air draws in vapor-rich, warm air off the ocean, essentially forming a heat engine. So once these things get going, they just feed off of warmer ocean water. Hurricanes expand outward, limited by availability of warm water. They are large enough to be spun by the Coriolis effect. Hurricanes move across ocean basins driven by atmospheric currents caused by differential heating from the sun, right? So all of the most direct sunlight is hitting at the equator, so this is where we're generating our hurricanes. Hurricanes occur between the subtropics and the equator, where the ocean waters are warm enough to drive this engine. And each hemisphere has a hurricane season. It's called something different, right? We call it hurricane season. In Japan, they're called typhoons, but it's the same thing. Okay, here are the different categories. They're all based on wind speed and predicted damage. So if the wind speed is greater than 39 miles per hour, it's called a tropical depression, okay, not a hurricane. If the wind speed is 40 to 74 miles per hour, then that's considered a tropical storm. Once the wind speeds hit 75 miles per hour, then it's considered a Category 1 hurricane. And it will be considered Category 1 with wind speeds from 75 to 95 miles per hour. So this is insanely fast, right? This is freeway speed and much faster than I would ever want to go in my car, just for a Category 1. So can you imagine when these winds pick up debris and that gets flung around the place? It can do a lot of damage even just with a Category 1. So the storm surge is this wall of water that gets built up along in front of the hurricane. So it pushes in all of this water before the hurricane hits land. So for Category 1, it's a 4 to 5 foot storm surge. And this is the level that Katrina was when it hit Florida. Once it hit the Gulf, where it was nice and warm, it picked up quite a lot of power from that warm water. Okay, Category 2, wind speeds of 96 to 110 miles per hour with a 6 to 8 foot storm surge. So I don't know about you, but I would be underwater with that storm surge, so you'd want to get out of the way. Category 3, winds of 111 to 130 miles per hour with 9 to 12 foot storm surge. So when Katrina hit Louisiana, this is what they had. They had a Category 3 hurricane. That's what the levees along the Mississippi River were built to withstand, nothing more. And they did not withstand it. That's part of the devastation that hit New Orleans was from the failure of the levees. So Category 4 is wind speeds of 131 to 155 miles per hour with 13 to 18 foot storm surge. In 1900, there was a huge hurricane that hit Galveston, Texas. That's a historical event. There are a lot of good books on it if you're interested. you can find those. So just look up the 1900 Galveston hurricane. Category 5, winds greater than 155 miles per hour with a greater than 18-foot storm surge. That's what Hurricane Andrew was in 1992, if you were around for that, or Wilma in 2005. So when you hear them talking about the different categories of hurricanes, or if something drops out, if it was a hurricane and then it drops down to being a tropical storm and a tropical depression, now you know what's going on. Okay? It's just a change in wind speed, and that has to do with how much water vapor, how much warm water is there to fuel the storm. Here is a map of the cumulative tracks of all the tropical cyclones during the 1985 to 2005 time period. So what do you notice? Is it random? Are they absolutely everywhere? What I would like for you to notice is that they tend to go along the equator, right? Whether it is south of the equator or north of the equator, that's where they're starting out. And they travel across the ocean until they hit another bit of land and they work their way up towards the pole. Okay, that's the typical pattern. Thunderstorms. Observe the motion of air and water in a supercell thunderstorm and related tornadoes. So what's going on here? Thunderstorms are columns of turbulent, moist air with variable amounts of lightning, thunder, rain, hail, and wind. Usually, they develop a flat-topped anvil shape. Supercell thunderstorms are capped by a rounded upper dome indicating strong updrafts. Downpours commonly associated with supercell thunderstorms can be very, very heavy. Okay, so you have a lot of rain. Updrafts, which are just upward moving winds, are what spawn tornadoes. So the air gets rising and cycling upward, and then it gets out of control and forms a tornado. Lightning results from electrical currents within the storm, and they also cause microbursts, which are these very rapid, strong, downward moving winds that typically produce winds that move in a straight line rather than rotating. So it's just a rapid drop. The air is very cold and boom, it just sinks down. And they move so rapidly that they can flatten trees or structures. Tornadoes and supercells. So what is a supercell? A supercell is an unusually strong thunderstorm that generates tornadoes. Now, it doesn't always generate tornadoes. You can have a supercell thunderstorm without any tornadoes. But that is the type of storm that will generate tornadoes. Okay, what is a tornado and where do they strike? Tornadoes are violent, rotating, funnel-shaped columns of rising air that extend to the ground. They generally form at cold fronts where cold polar air encounters warm tropical air. Tornadoes produce high winds up to 300 kilometers per hour. Okay, we thought that the hurricanes were fast. This is even faster, but they don't last as long or go over as wide an area typically as hurricanes. This year has been pretty exceptional for breaking that rule. They mostly occur in central and eastern U.S. because of that interaction between the cold polar air and the warm, moist air moving northward from the Gulf of Mexico. Okay, so it's like the perfect storm there, fueling supercell thunderstorms that lead to tornadoes. Okay.